At this point, we've had plenty of practice using substitution in indefinite integrals. That means integrals with no bounds. So when we're dealing with substitution in definite integrals, where we have a lower and upper limit of integration, we are going to do it the same way. The only thing we need to remember is that however we've chosen our u, in this case we say g of x, that inside function, the part of the composition that's inside, if we let that equal u, then our bounds need to also change to be in terms of u. So you would plug a and b both into your g of x function to get new u bounds. All right? You do have the option to convert your function back into x's and leave the bounds the way they are initially given as a and b instead of changing them into terms of u. But it just brings in some unneeded confusion. So as we work through these problems, whenever we do a u substitution, we're going to make sure that we remember to change our bounds to also be in terms of u. So let's look at some examples. So here, we are going to evaluate the definite integral from 0 to 1 of r times the square root of 1 minus r squared, integrated with respect to r. So when we have radicals, we turn those into rational powers. So I'm going to rewrite this as 1 minus r squared. I'll make it to the 1/2 power. And so since we've had so much practice, most of you can probably see that we're going to come through here and we're going to say let u equal 1 minus r squared. And that means then du, the derivative of u with respect to r, would equal negative 2r. So we'll rearrange. Du is negative 2r dr, or negative 1/2 du is r dr. So I have my r dr. The only thing that's new here is we want to make sure and pay attention to our bounds. Currently, these bounds, 0 and 1, are in terms of r. The function was given in terms of r. These represent r values. I need u values. So, if r equals 1, then u equals 1 minus 1 squared, or 0. And if r equals 0, then u equals 1 minus 0 squared, or 1. So when I do my substitution, this is going to become the integral 0 turned into 1, 1 turned into 0, of u to the 1/2, and r dr was equal to negative 1/2 du. So it's just very important that you note the bounds changed. 0 turned into 1 and 1 turned into 0. And it's just a coincidence that they flip-flopped here. So let's look at simplifying this. That negative 1/2, I can put that in front, right? So I have negative 1/2, the integral from 1 to 0 of u to the 1/2 du. And you don't have to do this, but it's common practice and we like to keep things in order. So you'll notice my bounds are not the way we generally want them. The lower limit is actually larger than the upper limit. But one thing we know is I can reverse my bounds and I can turn that into 1 and 0, but that would involve me negating the entire integral. So those two negatives cancel out and I have positive 1/2, the integral from 0 to 1 of u to the 1/2 du. And this is easy to integrate. We get 3/2 in the exponent, so that is 1/2 we have 2/3 u to the 3/2. And because this is a definite integral, we do not write plus c. We just write our upper and lower bounds of integration. Now, those bounds are in terms of u. Because I changed them, they're not the original bounds. They're now in terms of u, and I do not need to convert back to x. So looking at simplifying this, the 1/2 and the 2/3, that's 1/3. I have u to the 3/2 from 1 to 0, which is 1/3, 1 to the 3/2 minus 0 to the 3/2. And my answer here is 1/3. 1/3 is the exact value of this definite integral. Let's do another example. Here we're going to evaluate the definite integral from 2 pi to 3 pi of 3 times cosine squared x sine x dx. So before I start trying to do any substitutions, I'm going to rearrange using some properties that I know. That 3 can come in front. That is 2 pi to 3 pi. I'll rewrite the way cosine squared x looks as cosine x quantity squared sine x dx. So I'm going to determine, I'm going to say let u equals cosine x. If u is cosine x, then the derivative of u with respect to x, the derivative of cosine is negative sine x. So I see that sine x dx there. I see my cosine. So let me rearrange this. This becomes the derivative of u, or equals negative sine x dx. And if I multiply by negative on both sides, that would be negative du equals sine x dx. So we also need to make sure we change our bounds. If x is 3 pi, then u is cosine of 3 pi. And cosine of 3 pi, that's going to give me that u equals -1. And similarly, if x is 2 pi, then u being cosine of 2 pi, that would give me u equals +1. So by substitution, this becomes 3. My bounds change, 1 and -1. Make sure you get them in the correct spot for however you did your substitution. I have u squared, and sine x dx is equal to negative du. So I'm going to put my negative, I'm going to just go ahead and throw that in front. All right, so notice your bounds in this situation are not in the same order. So I'm going to flip the bounds. Flipping the bounds would negate everything, and this is +3 from -1 to 1 of u squared du. So 3 remains when I integrate u squared. That is u cubed over 3, evaluated from 1 to -1. My 3's will cancel, and this is u cubed evaluated from 1 to -1, which is +1 cubed minus -1 cubed. 1 minus -1 is 2. So 2 is my answer here. +2 is the value of my definite integral. So I'm going to include one more example in this video. For this example, we're going to evaluate a definite integral again. This integral will be 1 to 9 t times the square root of 4 plus 5t dt. So I'm going to rewrite that as a 1/2 power for my radical. My u value is going to be what is in the exponent. So we'll say let u equal 4 plus 5t. That means the derivative of u with respect to t is 5. Or du is 5 dt, or 1/5 du equals dt. So I have this extra t in here. I'm not really sure how to deal with this t value. Okay? So let's look at what happens. I'm going to go ahead and change my bounds while I'm doing this as well. So notice these two bounds, 1 and 9, are in terms of t. If t equals 9, then u would be 4 plus 5 times 9, which is 49. 45 plus 4 is 49. And if t is 1, then u equals 4 plus 5 times 1, or u equals 9. So let's look at what we have. We have the integral from 9 to 49. I still have this t. What's inside my parentheses, that is u to the 1/2. And then dt is equal to 1/5 du. I have a t in there. I want everything to be in terms of u. Well, what if I take the way I defined u and I rearrange it and I say, well, up here we can say t would equal u minus 4 divided by 5, or 1/5 of u minus 4. So I'm going to use that substitution, 1/5 of the quantity u minus 4, and that's going to give me the integral from 9 to 4, 1/5 u minus 4. I still have my u to the 1/2, and I have times 1/5 du. So this is a point where I would encourage you to pause the video and make sure you understand the way I've rearranged this problem. All right, so thinking about this, those 2 times 1/5, they can come out in front, and I have 1/25, that should be 49. The integral from 9 to 49 of u minus 4 times u to the 1/2 du. Now at this point, it looks kind of similar to what I started with, but I have one term raised to a power, and I can distribute that to both of these two terms in the parenthesis. So this is 1/25, the integral from 9 to 49 of u to the first times u to the 1/2 is 3/2 minus 4u to the 1/2. All of that is what we are integrating with respect to u. At this point, I can use my power rule twice. So I have 1/25 in front. U to the 3/2, if I add 1, that's going to give me 5/2. So I have 2/5 u to the 5/2 minus 4. And if I add 1/2, or I add 1 to 1/2, I get 3/2. So that would be times 2/3 u to the 3/2. And all of this is going to be evaluated between 9 and 49. So 4 times 2/3, this 4 times 2/3, that's actually 8/3. I'm going to simplify that in here and just go ahead and write 8/3. So I've got 1/25, 2/5. I'm going to plug in 49 first. So 49 to the 5/2 minus 8/3, 49 to the 3/2. So 2/5 is there. And then I'll evaluate at 9. So minus all of 2/5, 9 to the 5/2. Minus 8/3, 9 to the 3/2. And so, this is ugly for us to deal with or simplify, but very doable. 1/25. I have 2/5. 49, the square root of that is 7. And 7 to the 5th is 16,807 minus 8/3. Again, square root of 49 is 7. You cube it, you get 343. Minus, I have 2/5. Square root of 9 is 3. 3 to the 5th is 243. Minus 8/3. Square root of 9 is 3. 3 cubed is 27. And I'm just going to jump to the answer. We end up with 86,744 over 375. That is the value of our definite integral. So we've done 3 examples in this video where we solved definite integrals where we had to use substitution and change our bounds. And as long as we change our bounds when we're doing our u substitution, we don't need to go back to the original variable in order to evaluate. So it really shortens the process for us. You can go back, but again, it's going to make that expression that you're trying to evaluate in this step, it's going to make that much uglier. So I always recommend changing your bounds right at the beginning, and then you have something relatively simple to evaluate at the end.